And we're back and better than ever to wrap up 16.1, where we're dealing with properties of solutions. Right now we're in the middle of our discussion of the effect of pressure on solubility, and it's governed by Henry's law. We've just done a practice problem where we determined a new solubility as we lowered the pressure of a particular system. So let's talk about why pressure plays an important role. Let's go with a brown color here. We're going to deal with pop. So here's our pop bottle. We'll make it a cola of some type. All right, there's your irregular shaped bottom, and we'll go up, something like that. And here's our screw top, and we'll make that a red color. We're not plugging any particular brand there. We'll let you make your own decisions. And we'll make another pop bottle, like so. And something like that. Okay, so let's just say we have the pop about 3/4 filled on the first bottle. And there are going to be a lot of gas particles. Let's go with that in blue. There's going to be gas particles down here. Now when they're dissolved, you can't see them necessarily. If you look at a pop bottle, now sometimes they're fizzing, but if they've been undisturbed, you won't necessarily see anything in there. What happens is the particles will escape into this area above the pop itself. And what happens is there's an equilibrium that exists where you have equal numbers of gaseous particles going into the liquid particles going into the gaseous phase as you have crashing down into the liquid phase out of the gaseous phase. And so with that, you have a equilibrium and a particular pressure. Now, under high pressure, you're going to be forcing a lot of gas down into the pop at high pressure. What happens at low pressures means you have very few particles up top here, and that means that you'll have more particles that it can escape up into that gaseous area that's above the pop. So the higher the pressure is, the more gas you can keep forced down into the solution. The less the pressure is up top, the more the gas can escape into that open area. Now what happens with pop bottles is that when you buy the pop, you have a high pressure sitting above the pop itself. But what happens is as soon as you open up that cap, let me draw in the second one here. Let's say here's our pop there, and we'll put our gaseous particles here. All this gas that was trapped on top of the liquid now can escape. And when that happens, you're going to lose all your gas. Let's get our eraser here. You're going to lose all the gas particles from inside of that container. Well, what's going to happen, let's go back to our pen. What's going to happen is that the gas bubbles or the gas particles that are down here now have no pressure to hold them down, and they're going to migrate towards the top. And sometimes that happens very violently if this thing has been shaken up pretty good. Otherwise, as soon as you open up the bottle, you hear the fizz, psh, the gas escapes from the bottle, and then the gas bubbles that were trapped in the pop itself leave the bottle, or at least leave the solution, and start collecting up here. Now if you don't put the cap back on, of course that's going to escape. But if you go ahead and put the cap back on, what's going to happen is it's going to reestablish a new equilibrium, and then it's going to hold more particles down there. But as soon as you take that pop lid off, psh, the gas escapes again, and then you get more of the gases leaving the solution. Now, there's only so much gas or so much carbonation in the pop. So every time you open this thing up, the more and more carbonation leaves. The other thing that happens is as soon as you open up the bottle itself, you'll lose the seal, and so even though you put the lid back on, it's not as tight a seal as it was originally, and so gas is going to leak out, and eventually the pop will go flat. Now these things aren't perfectly sealed, so if you have a pop bottle that's sitting years and years and years and years, then eventually that gas can escape, and you will lose your carbonation. You'll open up the bottle of pop, but yet it will be flat pop. So the bottom line is the higher the pressure is, the more particles you can keep forced in the solution, and the higher the solubility is. The lower the pressure is, the fewer the particles you can keep in the solution. So let's go ahead and wrap this thing up with one last problem. It says the solubility of gas in water is 0.16 grams per liter at 104 kilopascals. What is the solubility when the pressure of the gas is increased to 288? So we'll go with our equation here. Let's change this back to orange. There we go. So we have S1 over P1. The original solubility over the original pressure will equal the new solubility over the new pressure. Now, because we're increasing the pressure, we would predict that the solubility would increase. So let's see what happens. You have 0.16 grams per liter over 104 kilopascals. This is grams per liter. That's going to equal our new solubility over the new pressure, which is 288 kilopascals. Of course, to solve for this, we're going to have to move the 288 kilopascals over by multiplying. So these terms divide out top and bottom, both the units and the number. Over here, the kilopascals divide out with kilopascals top and bottom in that fraction. And so now if you take your 288 times 0.16 divided by 104, you get 0.44 grams per milliliter. So S2 is going to equal 0.44 grams per liter. Excuse me, not grams per milliliter, grams per liter. So in the first sample, as you decrease the pressure from 3.5 to 1 atmosphere, the solubility decreased from 0.77 down to 0.22. In this case, we increased the pressure, so therefore the solubility increased from 0.16 up to 0.44 grams per liter. That concludes 16.1.